This video is about Radian Measure. Up until now, we have been measuring angles using a degree measurement. And as we move on in our mathematical career, we typically use radian measures for angles. So an angle with its vertex at the center of a circle that intercepts an arc on the circle equal in length to the radius has a measure of 1 radian. So here's our circle centered at the origin, and here's our radius r, and the length of this here, put it another color, the length of this here is called our arc length, and if our arc length is equal to our radius, then the measurement of that angle theta is 1 radian. We can now say that since the circumference of a circle is 2 pi r, that's all the way around the circle. If we divide by r, then we get 2 pi radians is 1 revolution. Okay. This measurement here, 2 pi, is equivalent to 360 degrees. But in radians, we say 2 pi. We use this idea here, 2 pi radians equals 360 degrees, to come up with some conversions. So if I divide both sides by 2, I get pi radians is 180 degrees. That means that the ratio pi over 180 degrees or 180 degrees over pi are both equivalent to 1. So to convert a degree measure to radian measure, we're going to multiply by pi over 180 degrees. In this case, we're going to get 135 and 180 are both divisible by 45. We're going to get 3 pi over 4. Now, we typically leave the pi in there because that makes this exact, but if I wanted a decimal approximation, I could do that as well. In this case, that would be approximately 2.356. So both of these are radians. We don't have to write radians afterwards. If we're working with angles and there is no degree symbol, then the assumption is that it is radians. So we'll do the same thing here with 321.5. We'll multiply by pi over 180. And in this case, I probably, since I'm working with decimals anyway, I would probably go ahead and put the pi in there and get 5.61. And again, I don't have to say radians. When we look at the next two examples here, we want to be able to convert radians back to degrees. And in that case, we want to multiply by 180 degrees over pi. That way the pi's will cancel. In this case, we have 3 going into 180 60 times, and we get 300 degrees. Similarly, converting 3.6 to radians, I'm going to multiply by 180 degrees over pi, and that's going to give me 206.26 degrees, approximately. And again, I'll just say, if no unit of angle measure is specified, then the radian measure is understood. So I know, as on some previous videos, I might have harped on you and said, if you mean degrees, you have to put degrees, because sine of 4.5 degrees is very different than sine of 4.5. If I leave the degree measure off, I leave that symbol off, second one is just radians. All right, so we use Radian Measure to solve lots and lots of application. And the first one that we do is called arc length. And arc length, we kind of talked about it before, but arc length is some measurement on the outside of the circle. So the length of the arc. When we want to find arc length, the formula is S equals r theta. This theta, however, must be in radians. So we're going to take, for this example, a circle has a radius of 12.5, and the length of the arc intercepted by the central angle of 5 pi over 6. So that is in radians. So we are just going to multiply 12.5 times 5 pi over 6. And that's going to give me 10.42 approximately pi. And because my radius was measured in centimeters, it's centimeters. Let's see if we can do that again. This one's slightly different. A circle has a radius of 8.65 centimeters. We want to find the length of the arc intercepted by a central angle measure of 220 degrees. So here's our 8.65 centimeters. If from here to here is 180, we're going to go from here to here is going to be about 220 degrees. Now remember, first of all, we're finding this arc, the larger arc here, that S equals r theta, that formula, the theta has to be in radians. So the first thing I need to do here is change my 200 degrees to radians. So we're going to multiply by pi over 180 and get 11 pi over 9. So using this formula now, we get 8.65 times 11 pi over 9, which gives us approximately 33.2 centimeters. So almost the same, but we had to here first change it to radians. This next example, a little bit different. We have some motion going on here. So let's say we have a pulley, and on that pulley is a rope that holds up some weight. So we can see that from here to here that the rope is attached to the pulley, and we're going to raise the pulley 11.4 centimeters where we want to raise it, and the rotation is 51.6. So we want to know what is the radius of this pulley, what is r, if the arc length is 11.4, so that would be from here to here, and the angle theta is 51.6 degrees. So in this particular case, using the formula S equals r theta, we happen to know the S, which is 11.4. We're looking for the radius, and we have theta, but it's in degrees and we need it in radians. So I'm going to multiply by pi over 180 and put that in my calculator, and I get approximately 0.9006. If you want to be more exact, leave all of those decimal places in your calculator. 9006. And then we're going to divide both sides by 0.9006. And I am going to use the entire decimal. And I get 12.658. 12.658. Still rounded, but I didn't use any rounded values as I went. And since our arc length was measured in centimeters, this is measured in centimeters. All right, here's another example. Let's say we have 2 gears, and we're going to say that the radius of this inner gear, this smaller gear here, is going to be 8 centimeters. We want to find the radius of the larger wheel, which we will call R, capital R, because it's big, when the smaller wheel rotates 80 degrees and the larger wheel rotates 50 degrees. And so this one in the little thing in here is going to be 80 degrees. Okay, so what you should notice is the teeth of these gears connect, and that when this moves, when the large one moves this much, this arc, then that same arc has to be on this one here. So we want to find out what is the radius so that that is the case. So I'm going to think of this as 2 different arc length problems. For this large angle, or large gear, I'm going to say S equals R theta. And for this small gear, I'm also going to say S equals R theta. Now, we notice that 80 degrees and 50 degrees are not in radians. So I'm going to change 80 degrees to radians, and I'm going to get 4 pi over 9. And I will do the same thing with our 50 degrees, and that's going to give me 5 pi over 18. So for our large arc, S is capital R, and then our theta is the 50 degrees, or 5 pi over 18. For our small gear, our radius is 8, and our theta is 4 pi over 9. Well, we know that these 2 arcs have to be equal. So we're going to set those 2 equal. This one here is going to become 32 pi over 9 equals 5 pi r over 18. So I'm going to multiply both sides by 18 over 5 pi. That will leave the capital R by itself. The 18s will cancel and the 5 pi's will cancel. So we're going to get R equals, well, here the pi's cancel, and 9 goes into 18 twice, so we get 64 over 5, which is 12.8. And because we're measuring this in centimeters, this is 12.8 centimeters for the radius of the larger gear. All right, the last applications that we do with area of a sector are finding part of the circle. So when we're talking about the entire circle, the area is pi r squared. And when we talk about just part of that, that's a sector. And that formula, area of the sector, I'm going to write it like this, is 1/2 r squared theta. So why is that true? Well, if our angle in here is theta, theta is to 2 pi. So theta to the whole circle is the area of the sector times the area of the whole circle, which is pi r squared. So if we're solving for the area of the sector here, we're going to multiply by pi r squared on both sides. And we're going to get the pi's canceling. So we're going to get r squared theta over 2, or 1/2 r squared theta. So this is the formula we're going to use. And just like before, we have to have theta in radians. So when I look at this first example, I want the area of a sector of a circle with a radius of 12 centimeters and a central angle of 112 degrees. So I'm going to call this angle theta 112 degrees. Well, again, we have to change our 112. So 112 times pi over 180 is going to give us 28 pi over 45. And then we'll use our formula. Area of a sector is 1/2 r squared times theta, 28 pi over 45. And we'll end up with 224 pi over 5. And since this is area and our radius was in centimeters, the units here are centimeters squared. So if you were doing this, you could have said, this is 144. 12 squared is 144. 2 goes into 144 72 times. So 72 times 28 divided by 45 gives you the 224 over 5. Okay, last example is we want to find the radius of a circle in which a central angle of pi over 6 determines the sector of area 64. So again, we're going to use this formula that the area of a sector is 1/2 r squared theta. And in this case, we know the area of the sector is 64. We're looking for our radius. Our theta is pi over 6 over 2. So I'm going to multiply both sides by 2. So that's going to give me 128 equals pi r squared over 6. And then multiplying by 6, or let's do this. Let's multiply by 6 over pi. And that's going to give us r squared is 768 over pi, or r is approximately 15.64 inches. And since this is a radius and it's a linear measurement, we have linear measurement there. That concludes this video on radians and applications of radian measure.